Good morning and welcome to this special seminar with Dr. William Cheung. Before we start, I would like to acknowledge that we are gathered today in the traditional territories of the coastal Salish people on whose lands the SFU campus resides. My name is Nastenka Calle. I am the program manager for the Pacific Institute for Climate Solutions. PICS, as some of you may know, is a research institute. It's a collaboration of 4 universities led by the University of Victoria and works in close collaboration with SFU, UBC, and UNBC. PICS share a global vision of net zero greenhouse gases emissions by mid-century while adapting to the changing climate. So, as part of our mandate is to do outreach, communicate the climate solutions, and promote collaboration between our university partners. So this time we have our guest speaker, Dr. William Cheung from UBC, and he's going to be talking about the ecosystems in the marine environment and how fishes are being impacted and what we can do about it. What are the solutions that they are trying to find out to this problem? Dr. William Cheung, he's an associate professor at the Institute of Ocean and Fisheries at UBC and is director of the Nippon Foundation, UBC NEROS program. His main research areas include understanding the responses and vulnerabilities of marine ecosystems and fisheries to global change, and examining trade-offs in managing and conserving living marine resources. His work cut across multiple disciplines, from oceanography to ecology, economics, and social sciences, and range from local to global scales. William has published over 150 peer-reviewed publications, including papers in leading international journals. William is also actively involved in international and regional initiatives that bridge science and policy. For instance, he was a lead author in the Working Group 2 of the 5th Assessment Report of the Intergovernmental Panel on Climate Change, the IPCC. A coordinating lead author of the Intergovernmental Platform on Biodiversity and Ecosystem Services and Global Biodiversity Outlook. Before we start, I just forgot, I would like to welcome also the people, the audience that are joining us via the webcast. I know there was a lot of interest from DFO and the Fraser Valley to attend remotely. So hopefully, guys, you are joining us, and apologies, I know there was a little problem on the screen, so there is a little glitch there, so hopefully it can be resolved. We're working on that. And with that, I would like to welcome William. We're really, it's great having you here at the SFU. Please.
Thanks very much. Just would like to thank Nastenka and PICS to invite me to come to this seminar. I've been here SFU a couple of times, but this is my first time that speak in here with work with a lot of colleagues here, and some of the friends are here. So it's great to be here and to share some of the works about climate change and the effects on fish and fisheries with you. And then maybe after the talk, we can have some discussions about some of the things that I talk about, and maybe have some exchange of ideas. Oops. Let me stop this, and then so before I start, I just want to give you an introduction of the group that I have in UBC that is called the Changing Ocean Research Unit. This is basically the research unit that is based in the Institute for the Oceans and Fisheries in UBC. Overall, our unit focus on looking at predicting the future oceans and the climate change. That's our vision. And the way we do it is to try to use scenarios and models to actually inform us about the possible futures. The changes in the ocean, the changes in the fish, as well as changes in people who are dependent on the fish. and then we want to through that try to understand the past, current, and future changes of the marine ecosystems and the ecosystem services that the oceans provide us under global change. And then hopefully from this scientific work, we can provide some useful information that can inform policy from global scale to some of the national or local scale. The works that I'm going to present is not my own effort. It's a collective effort from the whole team, from postdoc, research associate, students, and administrative colleagues. So just want to first of all acknowledge their contributions to all the works first. These are two sets of numbers, 1 billion versus 9.7 billion, 700 billion versus 100,000 billion, and 0.2 billion versus 700 billion. Do you know what these two sets of numbers means?
To do with the Earth's population.
Yeah, it's very good. I think that's one aspect of it, which is the first row. The first row will send the past populations, which is around in 1800, there's only around 1 billion people, and it's projected that by 2050, we will have 9.7 billion people on Earth. And with this growing population, there is also an immense improvement in our well-being and wealth. So the second set of numbers represent our gross domestic product, from 7 billion improved to and project to around $100 billion by in the next few decades. And this, a lot of it is made possible by the utilizations of new energy sources, and particularly fossil fuel, that has powered a lot of innovation, development of machinery that can provide more efficient ways to produce things and provide services. But then associated with that is also byproducts, and one of the key byproducts from the utilizations of fuel, fossil fuel, is carbon dioxide, another greenhouse gas. So the third set of numbers will send a huge increase in the amount of carbon dioxide that we have emitted into the atmosphere. I just look at the cooling curve, which is the monitoring, the monitoring of carbon dioxide concentration in the atmosphere in Moanoa in Hawaii, and we have passed 400 ppm. And I just look at the figure that they produced that shows the carbon dioxide concentration in the last 100,000 years, and it's just amazing that you see this low line, and then in the last couple of centuries, you see this almost strict increase in carbon dioxide. This is really impactful figure that highlights how quickly we have emit the amount of carbon dioxide that we have now in the last century or so. And associated with all these changes is also the ability to utilize natural resources with more machine, more energies that allow us to utilize other natural resources. And one of the aspects that my works focus a lot on, and is really important for us, is fisheries resources. This is a figure that shows the changes in the annual productions of global fisheries catches from 1950 to now. It is based on the CR1S project's global fisheries catch dataset that my colleagues Daniel Poli and Josh Seller produced and his team produced in UBC. So basically, it shows that global fisheries catches increased really rapidly until the 1990s, and then it started to level off. And in a sense, it's actually decreasing in the last couple of decades. But when we look at the fishing effort, which is the amount of energy and fishing boats and technology that we put in catching fishes, it actually increased continuously since the 1950s, and particularly the rate of increase continues after the 1990s, even though catch decreases over that period. So this is the first sign that we have already reached the overall capacity of the oceans to provide us with fishery resources, at least for traditional fishery resources that we have been utilizing in the last few decades. It basically shows that with increasing effort to catch fish, we would not be able to catch more fish. But in some cases, because of overexploitation, actually fish catch decreases. even though we talk a lot about prospect of aquaculture, and in this case I focus on mariculture, which is the production of seafood from aquaculture, it's only a small proportion of the global seafood production, at least for now. And even if we add that proportion to the global fisheries catches, it can just maintain the overall level of seafood production to stable in the last few decades. And there are current estimates that around 30 to 60% of the global fish stocks are overexploited. So that poses a question. If that's the past and current trends, what will be the future? Will there be more fish or less fish available for us and other people to use and enjoy? We know that there are already lots of things that are affecting the ocean's ability to provide fish for us to generate fisheries productivity. We know overfishing, habitat destructions, pollutions. There's lots about talk about plastic, but then there are also other sorts of pollutions. And then lastly, in the last couple of decades, we realized that CO2 that we emit to the atmosphere is also affecting the ocean. And we know that the ocean is changing. The measurement shows that, for example, ocean temperature is warming up. And we know that these changes, much of it is driven by carbon dioxide and climate change. The oceans already is doing a really big job for us to moderate our climate. For example, it absorbs more than almost 30% of carbon dioxide that we emitted. At the same time, the ocean is a really big heat absorber. It absorbs almost more than 90% of the heat that we generated. So without the oceans, our planet would not be able to be suitable for us to live at all. But in doing so, in doing these big services for us, the ocean is also being affected. It's like going to see a medical doctor and trying to get some vital measurements of your that can indicate your health. We can also do that for the oceans, and some of the indicators that shows that the ocean's health may be affected by this carbon dioxide problem include ocean warming, ocean deoxygenation, and ocean acidification. There are already solid evidence that shows that global ocean heat content is increasing. There's a recent published data that shows that long-term decrease in oxygen content in the global ocean. And then there's solid record that shows that with carbon dioxide going into the water, the ocean is being acidified and the pH is decreasing. And these changes are projected to continue in the future under different emissions of scenarios of how we emit carbon dioxide. Particularly, these are the projected changes in different ocean variables using these big-scale global climate and ocean system models. And there are two lines here that project into the future. One is the red line, one is the blue line. These represent two emission pathways that are considered by the Intergovernmental Panel on Climate Change. And I will be referring to these two different scenarios a lot in my presentation. The red line represents the high emission scenario or the business as usual scenario. And the blue line represents the strong mitigation scenario, meaning that the global communities can reduce substantially their carbon dioxide emission, and at some point may actually even absorb carbon dioxide through some other processes that will lead to a low warming world by the end of the century. So that's a low emission scenario. And with all these changes in the properties of the oceans, it is affecting the marine ecosystems as well as the dependent communities. And in order to fully understand the implications of all these changes, we need to take this as a holistic approach in order to understand this problem. We need to understand the changes in the ocean, how that affects the biology of the organism. For example, the changes in growth, reproduction, mortality, and how that then affects the populations, their distributions, abundance, and how all this would then affect community structure, trophic interaction, and ultimately, it would then affect people who are directly dependent on fish stocks, such as fishermen and other resource users, and the economics of these sectors. At the same time, at the more broader level, other changes in the society, such as the use of energy, fuel price, and other food price, would also have an impact on the oceans. And so the interactions of which will emerge out in as an overall implications of climate change and CO2 emissions in the oceans and the ecosystem. So in my talk, I would divide into three parts. First of all, I will talk about some of the drivers, the key drivers of changes for fish and fisheries, and particularly I'm trying to tease out how much and how important climate drivers is affecting the fish and fisheries. And secondly, I will talk about some of the projections and the scenarios that we developed in order to understand the future vulnerability and risk of different fish stocks and fisheries in the world under climate change. And finally, I don't want to leave you with a really pessimistic view about the future, about the oceans. And we actually still have possible solutions to tackle a lot of the impacts that I'm going to talk about in my talk. So in the last part of my talk, I will suggest some of the possible solutions and particularly highlight some of our science that we have conducted and how we inform the effectiveness of those solutions. A big question at the starting point is we see changes in the oceans, depletions of fish stocks or changes in distributions of fish stocks, but how much of it is driven by fishing or how much of it is driven by environmental change? Because we know fishing is a big human activities in the ocean and is already driving a lot of changes in the ocean ecosystem. So in this particular analysis, my colleague Christopher Owen and I and other colleagues try to use the global fisheries catch data to see whether we can answer this question. So we look at the distributions of or the level of fisheries catches in different large marine ecosystems, as delineated by the line in the ocean here, and then we use statistical methods to try to see which indicators would explain most in terms of the patterns of fisheries catches in different large marine ecosystems. And we categorize the key drivers into three types. First of all is the drivers of changes in ocean productivity. So that's actually indicated by the relationship with core fuel A concentration. And then the relationship with fishing, correlated with fishing efforts. And then finally is the relationship with general ocean conditions, which is correlated with sea surface temperature. There are some ecosystems that we don't have sufficient data to classify them. So what we find is that overall there are actually a mixture of different drivers that are affecting the fisheries in different marine ecosystems. And a lot of this is driven by environmental changes, like, for example, the Pacific Northwest or the northeast coast of the Pacific Ocean. While in some cases, like Australia, it is largely driven by fishing effort. And one of the reasons for that is that Australia is still a developing fisheries, where the development of fisheries is pretty new. So the fishing changes in the fisheries is largely driven by the way that the fisheries is developing even now, compared to some of the other areas where fisheries have been well developed. So in this case, environmental change play a bigger role. We did a subsequent analysis looking at the temporal attributions of different factors, and what we've also find similarly is that in area where there are long history of exploitation, the fishery resources has been fully utilized by fisheries, and then it becomes more sensitive to environmental change because the changes in fisheries becomes a less important aspect, while changes in environments would then affect the capacity of that part of the ecosystem to provide fisheries catches to the fisheries. So overall, this shows that there's a strong environmental signals in global fisheries catch data, and that the strength of the signals differ depending on the ecosystem type as well as the history of fisheries development. We also did quite a lot of work trying to link changes in ocean productivities to fisheries productivity, because there's been decades of theoretical work that try to establish the linkages between these aspect through the trophic dynamics or trophic energy pathway. So in this case, changes in phytoplankton protections through the marine food web should affect changes in fisheries catches, some level of capacities of providing fisheries protection. And we use, again, global fisheries catch data combining with the observed primary protection data, as well as some of the model simulations in estimations of the coastal primary protection data. And what we find is that there is a strong and significant relationship between phytoplankton protection and overall fisheries catch protection at the ecosystem level. And one thing that we find also quite interesting is that the relationship between phytoplankton protection and fish protections, although it is strong, but then it varies between ecosystem. And one thing that we hypothesize that affects that relationship is trophic transfer efficiency and the amount of carbon export to the deeper ocean that would then fuel the energy source for the trophic food web in the sea bottom or the demersal part of the food web. So by adding these two components into the relationship, we are able to explain much more variations in the fisheries protection compared to previous effort in the last few decades that shows like a moderate to weak relationship between phytoplankton to upper trophic level protection. So the overall message in this is that there is a strong relationship between phytoplankton protection and upper trophic level protections, and that is mediated by some of the properties of the ecosystem, such as trophic transfer efficiency and how much energy is exported to other parts of the ecosystem. And so it also means that when climate change affects phytoplankton protections, it will also have a big influence on the upper trophic level protection. But we care more than just biomass protection. We care about the kind of species that we're getting because they have different values, particularly different cultures will value different fish differently. These are the different dishes, the Chinese dishes, and the groupers we eat it in a traditional banquet, so we don't normally eat it at home. The flatfin beams, which is a kind of a daily fish, at least for when I was young. My mom cooked it every day for me. It's now getting expensive because of overfishing. But still, it is kind of a normal everyday fish. And the squid is not eaten every day, but then it's also a common dish. So different kind of species, we value them differently. And so we also want to understand how different species are affected by climate change as well. And in fact, we know a lot about how different species can respond differently to environmental change. There are decades or even centuries of fundamental biologies that help us to understand how fish and other marine species would respond to temperature, for example. In general, marine species, which is ectotherms, they prefer a certain range of temperature. So as indicated by the figure on the left-hand side, the vertical axis is the performance of their biology, aerobic performance. And when temperature becomes too hot or too cold, their performance decreases. And at some point, the fish will die because it just cannot tolerate the high or low temperature. And other ocean changes, such as acidifications or deoxygenation, may actually reduce that performance, and in many cases make the fish even more sensitive to environmental change. And different species would have different preference to environmental conditions. For example, polar species prefer cold environment, tropical species prefer warm environment. But then, because they are also evolving with the properties of the environment, so for example, the polar environment and the tropical environment is relatively stable. They have very cold environment all the time or very hot environment all the time. So their biology do not have a lot of room to adjust to a lot of variation in temperature compared to species that live in, say, temperate regions where there's large seasonal fluctuations in environmental temperature. So they have evolved their biology to be able to deal with that. And that would have implications on the ability of different species to deal with warming and other environmental changes. And we also know that by knowing the environmental preference, we can also predict where the species will live, because in general they would prefer to live in area where their growth can be optimized. So from those kind of fundamental understanding about species biology, we can already draw some hypotheses of how species will respond to climate change, particularly warming or deoxygenation. So imagine that this is a distribution range of a species, like cod, distributes along a latitudinal gradient and a depth gradient. With warming and hypoxia, you would expect them to change their distributions, and with warming particularly, species you would expect to move to the species will move to high latitude region or to deeper water where they can find cooler environment to live. With this, there are all sorts of implications to marine ecosystems, to fisheries, and to management. So for example, the shift in distributions may lead to new interactions between predator and prey. It may also affect the performance or the value of a protected area, and particularly if the protected area is designed for protecting a certain species. And then, if cod is a valuable species, so when the distribution shifts across political boundary, which the fish do not respect, they don't need a passport to go to different countries. So this will generate a lot of dispute or argument and debate about the sharing of fishery resources. And all of these are already happening. It is not something that is hypothetical. But there are anecdotal information about species, for example, moving into our coast that may be related to warming, such as squid or ocean sunfish. During the warm year of the Pacific Oceans, we see some of these kind of tropical open ocean species appearing more often in our coast. And we also know that some of the salmon populations, particularly the southern parts, are not doing really well. And there are lots of scientific evidence that shows that warming is at least one of the reasons that attributes to the poor performance of some of the salmon population. And in fact, there are also solid scientific evidence that already shows this fingerprints of climate change effects in the oceans. This is a meta-analysis that is included in the IPCC report, in the fifth assessment report, that collate all the evidence, published evidence about observed range shift of species, and see how much of it is related to changes in ocean temperature. Basically, the vertical axis shows different taxonomic groups of marine species, while for species that are going to the right-hand side, it means that it is shifting towards cooler waters, or to, in this case, it is measured as a distance shift. So in general, on average, species are shifting at the rate of more than 20 kilometers per decade. But then there are lots of taxonomic variation, with some species such as phytoplankton shifting hundreds of kilometers per decade, while some of the other species are shifting at a much lower rate. But the overall message for this figure is that species are already shifting their distributions, and that such shift can be attributable to ocean warming. And with species reshuffling, we would expect that then the patterns of species biodiversity and species richness would change. And theoretically, we have solid background to establish that shift in patterns of biodiversity. So this is a study that we finished and led by postdoc Gabriel Recondor. We collated a global database of species distribution that range from phytoplankton, zooplankton, up to fish and marine mammals. It contains 100,000 species. And what we then use is to try to then, based on their distribution, infer their preferred temperature, as well as the breadth of their temperature tolerance. So how big is the range of temperature that each species can tolerate? This is a map that shows the preferred temperature and the breadth of the temperatures of different species. As you expect, for example, tropical species prefer warmer water, while tropical species and polar species tend to have much narrower breadth of the temperature tolerance. But what we later do then is to relate this to a pattern of species richness, and then try to compare whether the temperature or thermal properties of the species actually can explain patterns of biodiversity, particularly the latitudinal biodiversity gradient. And we find that these two variables alone, with ocean temperatures can explain most of the variation in species richness along the latitudinal gradient. And we compared that with other competing hypotheses, such as the mid-domain effect, and things like that. And we showed that the thermal strategies actually is much stronger explanatory power compared to other existing hypotheses that explain the ocean patterns of biodiversity. So with that, it also means that changes in ocean temperature would have a big effect on the patterns of species richness. And since we already showed that species are shifting their distribution, we should already be able to detect some of the changes in distributions already. And one of the ways that we try to do that is to use the global fisheries catch data, because it is global, it comes from the global oceans, because the current fishing fleets are already fishing in most part of the oceans. So what we did is we created an index called the mean temperature of the catch. So for each species, we use the mean preferred temperature, as I just explained, and to calculate the average mean preferred temperature of a fisheries catches from a particular area or in a particular year, weighted by the level of catches for each species. So in this case, for example, the blue fish means cold water fish, while the orange fish means the warm water fish. The fisheries catch with more blue fish means a lower mean temperature of the catch, while catch with lots of red fish means a high mean temperature of the catch. And then we plot it over time in different ecosystems as well as globally. What we find is that there is a consistent increase in mean temperature of the catch in the last few decades, and that such increase is significantly related to increase in ocean sea surface temperature, even after accounting for the effects of fishing and other oceanographic changes. In the tropics, it's a bit interesting because it is the warmest part of the ocean. So initially, we detected some decrease in the dominance of the cooler water species, the tropical species. But then after that, the mean temperature of the catch stabilized. It actually suggests that some of the cooler water species are already decreased, and while the leaving behind are those species that can tolerate the higher temperature. So that's why there is that leveling off the mean temperature of the catch. The next question then is what would happen in the future if global warming continued? How would the changes in the species compositions and even the level of fisheries catch would change in the next few decades or in the 21st century? And the things is for species is that they have experienced historical variability. It's not that they are adapted to a single temperature, so that it goes to it leads to a concept of emergence where species historically adapted to a particular patterns of variability. In the Pacific, for example, temperature changes over time, over years, over decades. But then the problems start to occur when when the long-term changes because of climate change actually exceed that variability. At the time at when these exceed is called emergent. So in this case, these kind of signals emerge from the natural variabilities indicated by the standard deviation. And that's create problems for species because they wouldn't be affected. And when we look at different ocean variables across in the global oceans, we try to detect the time of emergence of these ocean variables. The color represents at what year the ocean variables has already emerged out from the natural variability. Temperature, the bluer the color, the more near term it is. So temperature is, for most parts of the oceans, it will emerge now, or it has emerged now, or it will emerge in the next decade or so. For pH, it has emerged now. So like even in the last decades, pH already go beyond natural variability because of that strong chemical pathways of carbon dioxide going into the water, decreasing ocean pH. Oxygens is much more variable because of the secondary effects of the mixing and changes in the stratifications of the ocean layers and things like that. but there are some parts of the ocean that would have much earlier emergence in terms of deoxygenation. While primary production is much more variable. There will be changes, but the changes may not be able to be detected at the local level until further into the century. And one thing that we look at then is whether we will identify parts of the oceans that the combinations of ocean variables, the things that I just talked about, will be so new that it basically is a new environment. It's a novel environment characterized by temperature, or pH, or oxygen, primary production. And we find the existence of these novel habitats in the next few decades under the high emission scenario, for example. So this is indicated by this red color, what we call novel habitats or novel biome. And it starts to emerge out in the next couple of decades in the tropical Indo-Pacific region and then start to expand. And the problem for this is that these novel habitats is so new that it hasn't occurred in the last thousands of years. So it also means that species may not be able to adapt to this new environment. There may be some species that may be able to adapt to this new environment, but then it also means that the communities structure in those environments will be really different from what we are seeing nowadays. As we look at the amount of species that are currently living in that environment and the catchers that are living in those currently those environments that is expected to be novel, is going to increase really substantially. For example, by the end of the century, under the high emission scenario, 30% of the fisheries that we're catching now actually come from these novel habitats, while around 50% of the marine biodiversity is also coming from these habitats, because those are also the center of marine biodiversity. So that highlights lots of risk to fisheries and marine biodiversity with the creation of these novel habitats. Another way we try to characterize the future risk of impacts is to use more explicit simulation model. We have been developing a class of simulation models called the dynamic bioclimate envelope model in the last decade or so that try to capture changes in ocean conditions and how that affects the ecophysiology of the animals, as well as the habitat qualities that then affects the population dynamics, the distributions, and the movement of fish. And ultimately combining with changes in ocean productivities, we try to project changes in fisheries catches. So let me show you a few examples so that it gives you a more concrete idea of what this modeling work does. So I take the example of the Pacific coast of North America. So one thing that this custom model project is the changes in the distributions and the relative abundance of the species. So for example, based on the outputs, we can characterize the distribution centroid, so where the center of distribution of different species are and how they will shift over time. So this is for Pacific halibut that distributes along a longitudinal as well as a latitudinal gradient. And these points represent the projected changes over time. This is a dynamic simulation, so we are able to project their distributions every year. And this is a summary for a couple of decades until the end of the century. It shows that Pacific halibut distribution is projected to shift northward and westward, and basically following the topography of the shape of the continent. We have Pacific. This is sockeye salmon that also shifting forward. This is anchovy, sardine, and mackerel. Rockfish, which actually don't show a lot of distribution shifts. So therefore, and on average, when we look at 76 species in the Pacific Northwest, it shows a general forward movement around 500 kilometers by the end of the century. It also highlights the variation between species. So for example, the mackerel is a large pelagic mobile species, so they are able to shift in large distance in a short period of time, while species like rockfish, they don't shift that much, and partly is attributed for their low mobility. So there are also models also capture some of the differences in their biology and how they would respond to climate change. And when we repeat this kind of analysis with over a dozen of species of exploited species around the world, we are then able to characterize the changes in pattern of species richness in the world. In this case, the upper map shows area where there will be a lot of species moving into that area, what we call species invasion. And as you expect, with the decrease in sea ice in the Arctic, increase in warming, and increase in temperature, and thus improvement in the environmental conditions that are more suitable for the subpolar or the temperate species, there will be a lot of species moving into the Arctic region relative to the number of species that they currently have. While the area where species are leaving, characterized as the local extinction, meaning that the species are disappearing from that area relative to their initial species richness, those will be concentrating along the tropical area. And so you see that big band of tropical area. And if you remember, the novel habitats that I showed you earlier on coincide closely with this. So the models actually capture the predictions that these habitats become so new that the species will actually move away because they cannot adapt to that environment in the model. There are also high rates of local extinction in semi and coastal sea, such as the Mediterranean or the Arabian Gulf, where landward boundary prevent the species from shifting further, and thus they will be affected because they are trapped in that semi and coastal sea. And we also look at the changes in the fisheries catches in the world, because that's one aspect of things that our model projects. So over the thousands of species that we look at, we find a really strong relationship between projected changes in the maximum catch potential, which is the proxy of maximum sustainable yield for the global fisheries catch, and global warming, which is characterized by the amount of warming in the atmosphere. So for example, we are targeting a 1.5 degrees Celsius warming under the Paris Agreement, but then under the business as usual scenario, we are likely to go to 3.5 to 4 degrees Celsius warming by the end of the century. So comparing to these two scenarios, we see a large differences in terms of the changes in maximum catch potential. And on average, we are projecting that with every degree Celsius increase in warming, we are going to lose our maximum catch potential by around 3.4 million tons. Also, fisheries catch composition is going to change at a rate of around 6.7% in terms of the composition of the species around the world per unit degree of warming. And this is just a global average, but there are lots of regional differences. So for example, in the tropical area, that you expect that with the species moving away, there are lots of decrease in catch potential, highlighted by the red area here. While northern countries such as Greenland may gain by having more catch potential there. The economic impacts in terms of the revenue or the money that the fishermen get by selling their fish actually mimics those of the changes in fisheries catch potential. So it means that it creates lots of potential impacts to tropical countries like the Indo-Pacific region, West Africa, South Pacific region, and Peru. And economics and catch is not the whole story, because there are some communities in the world that are more strongly dependent on fish compared to the others. And so these are the, for example, this is a study that a collaboration with colleagues in Harvard and other colleagues that look at the linkages or the relationship between the climate change impacts on fish and dependency of different countries on fish as a source of micronutrients like zinc, omega fatty acid, iron. And we find that, for example, countries like Peru, West African countries, countries in the Pacific region are highly dependent on fish for their health. But unfortunately, it mapped really well with the projected area where there are high decrease in fisheries catches, which is indicated by the blue area. And also these areas are often developing countries where they may have a less capacity to deal with some of these impacts. And but developed countries may not be safe from all this because there are also variations in the dependency of fish within the population. So for example, in British Columbia, we know that coastal First Nations are much more dependent on their fish for both food as well as for their traditions and ceremonial purposes. So in these particular studies, master students, previous master student Owen Weldon and colleagues, we look at the fish that are important to First Nations, and we apply our modeling approach to look at how climate change will affect these species. And what we find is that majority of the species that First Nations would depend on for food and ceremonial purposes will be negatively affected by climate change. For example, we project Pacific herring to decrease by almost 50% by mid-century under the business as usual scenario. And then there's also regional gradients of impacts, with southern coast possibly being impacted more than the north coast. And one aspect of this is that because there are strong tie to a particular species for food capture method or for traditions, the ability for First Nations to adapt to some of these changes may be relatively smaller compared to, say, commercial fisheries. So now we are developing projects with Anne and other colleagues are trying to further understand the implications of these to the health and the well-being of coastal First Nations, and trying to also think further about how what they can do to adapt to some of these expected impacts. So I would then spend the last part of my talk to talk about some of the potential solutions. I've talked a lot about that the ocean is dying. So hopefully this part will give you some hope to stimulate some actions and enthusiasm about doing science that would inform this solution. And broadly, we can divide these solutions into two aspects. One is mitigation, and that is adaptation. So mitigation basically is the need to reduce carbon dioxide emission. And the good thing is we know the Paris Agreement has signed that, which set our really ambitious target. And we, based on our analysis, we know that that target, 1.5 degrees Celsius warming, would be really good for the oceans. So we did this analysis trying to compare the Paris Agreement scenario with the business as usual scenario. And if we look at, for example, the most affected areas, such as the Indo-Pacific region, with the Paris Agreement, there is still some impact, but really minor. 10% loss in fish. So if the fisherman is catching 100 tuna, now they catch 90. So although there's still an impact, but this is much more easier for them to adapt to that level of impact compared to the business as usual scenario where they will be losing half of their tuna, for example. And that's much more difficult for them to deal with. So by achieving the Paris Agreement, it will be largely beneficial to fisheries that are most impacted by climate change as well. And we also know that before I move to adaptations, there are also other solutions that the oceans can play a role in mitigation, like renewable energy. Particularly, we know that renewable energy can play a big role in reducing the whole carbon emission. Wind farm, tidal energy, and things like that. So later in this month, we will have a workshop that talk about what are the opportunities for ocean-based climate solutions, and PICS will be participating in that workshop, trying to explore some ideas of highlighting the importance of the oceans in this solution space. And in terms of adaptations, we actually know already a lot about the role of adaptations and how the ocean can play a role in it. For example, there are many studies that shows that by better protecting coastal habitats, it also helps to reduce the sensitivity of coastal ecosystem to climate change. There are many works on kelp and other coastal vegetations. A recent work done by my PhD student, Ravi, and he showed that in the Caribbean, areas or countries with bigger area of coral reef actually have smaller changes in the fish communities due to global warming in the last few decades. So the take-home message is that if the reef can be protected, and with a large area, it may also reduce the sensitivities of the coral reef and the fisheries to climate change. And so one way to protect habitat is by protected area. And we are on a good trajectories in setting up protected area. This is from a paper by Cheung and colleague that look at the global area that are designated as protected area in the last few decades, and we show that this is increasing. Although we are still short of the target of at least 10% that we are hoping under the Convention on Biological Diversity. And Canada is still short of that target as well, and the government is doing a lot of effort in trying to meet that target. So that's good. But then one thing that we also need to think about is climate change also affects the way we think about protected area and how it can be effective, because as I said, with changes in species distributions, it may also affect the effectiveness of the protected area. And if we hypothesize that if species shift their distributions in a distance that is large enough to go beyond the boundary of the protected area, it will then affect the effectiveness of the protected area. And with that, we did a small exercise and look at how the size of the protected areas around the world and see how many of them are able to actually capture the wind shift of the species. So we, for example, take the Northeast Pacific as an example and the protected area there. So with this projected wind shift that I showed you earlier on, for MPAs that have size that is bigger than the protected area, in the wind shift, you see that right now these are the areas that is needed in order to be able to capture the projected wind shift. But for 50 percentile of the MPA in the US, for example, no one is near to that size. 75 percentile of the MPA, all of them are smaller than that size. It is only until we add the national monuments in Hawaii that it is big enough to be able to capture the wind shift of the species. And that's not only, the US is not unique, it's the same as all over the world. This is looking at the distribution of the size of the MPAs around the world. And again, we show that the majority of the MPA around the world would not be able to capture the shift in species distribution. So this is a really simplistic way of looking at whether a marine protected area is adaptable to climate change or not, but it highlights kind of the risk or the vulnerability of existing MPAs to climate change. And we need to then stimulate more thinking about how we can design the MPA in order to adapt to this change. Do we need a bigger MPA, or do we need a better designed MPA with network that would capture some of the wind shift and impacts? And the last example that we'll go through quickly is that by improving fisheries management, we can also help improve some of the reduce some of the impacts from climate change. So, for example, this is a specific case study is looking at high sea or open ocean fisheries management, where, for example, good management in the high sea is supposed to then lead to spill over into the coastal zone. So it will help coastal countries to adapt to climate change impacts. We ran our models to test this or to examine this scenario. We protect or sustainably manage the high sea in the model and then see how the coastal state may fare under climate change. What we find in here is that the color represents the level of changes in fisheries catches. With good fisheries management in the high sea and the lower climate change emissions, most of the countries actually would be able to benefit and compensate for the loss in their fisheries catch in the coastal area, except for area in the Indo-Pacific region. And it means that those areas, because of that novel habitats, it is so bad that even there is a high abundance of fish in the high sea, like tuna, they would not go back into the Pacific area, but then they will move to other areas. So globally, there is a good effects of high sea management that may compensate for some of the loss from of catch in the because of climate change. But then there are regional benefits that are different. Still, the tropical countries may be the least who can benefit from this kind of intervention. So we need to think harder about how we can then help these most impacted countries to deal with this impact. So finally, this last slide, it's nothing scientific. If we did a small exercise that look at the tweets in a short period of time and try to look at the tweets that mention the ocean. So we look at the Twitter database and try to characterize whether a tweet is positive or negative. So meaning that whether there's a positive association of emotion or not when they mention about the ocean. So positive means when they talk about ocean, they also talk about joy, trust, anticipation, but the negative mean anger, disgust, fear, or sadness. And what we find is that most of the time, or majority of the time, when they talk about the ocean, it is associated with some positive aspect. And this provides perhaps some stimulations about or encouragement that the oceans to most people is a positive thing, and that in this particular case we can see that the oceans can be also a solution to this climate problem, and that people will also want actively to preserve the oceans because of that associations with all the positive feeling. So with that, I want to conclude that we are really at the crossroad for the oceans because of climate change as well as other ocean impacts. But we still believe that there are solutions, and this is also indicated by our scientific evidence. But then the gaps, the ability to reduce impacts with these solutions is actually decreasing. So the longer we wait, the effectiveness of those solutions will decrease. And at some point, even though we act, it will be too late. So there's a particular big urgency in identifying and implementing these solutions. And so hopefully with this, with more scientific work, we will be able to help inform the developments of these development pathways that are climate resilient, so that we can actually have a sustainable ocean that support the well-being of people. So thank you very much.
Thanks, William, for that. Just before we open to the Q&A, I just would like to let the online people know that they can send their questions to my email. It's over there. If you can see it in the webcast link, but just in case, my email is n_call@sfu.ca. And with that, please ask your question.
Yes.
Yeah, you had these theoretical predictions about where species might move, and one axis was latitude, but another axis was depth.
Yeah.
I was a little surprised about that because there's a lot of constraints about depth, like increasing pressure, decreasing light, and as a matter of fact, none of your data looked at that after throwing that idea out there. So I was wondering if you could develop that depth hypothesis a little. Has it been explored? Is there data showing it? Is there literature on it?
Yes, certainly there is empirical evidence that species are shifting to deeper water, and in fact, one of the professors here, Lidovi, has published a really important paper on that for the North Sea that shows the North Sea species are shifting to deeper oceans around maybe 3 meters per decade, and our models predict similar magnitude around 3-4 meters per decade to deeper water. But not all species respond in that way. And you're right that there will be constraints about that, and also the local oceanography will affect that. For example, there will be, in some cases, deeper water may be less oxygenated, so some more species may not be able to do that. So our models capture some element of that, like oxygen, temperature, obviously, and we have set up to a limit of how deep the species can go. They cannot go from a shelf sea to the basal area.
Yeah, because pressure and
Exactly.
and then the life of phytoplankton
Yeah.
as well.
And we know that pirate protection or export protection is also a strong constraint on that because of the amount of food that would then affects the amount of fish that can live in that area. So yeah, there will be constraint on that. So they cannot go indefinitely to deeper water.
Well, thanks.
Yes.
Currently in BC and across Canada, a lot of species are under management where they need an additional enhancement for things like hatchery. And you spoke a bit about biodiversity. And those practices currently, they do not select certain genetic background.
Mhm.
They try to be as broad as possible. But with your prediction program and what you've already found across all the different oceans, would you suggest it's better to select for a certain genetic background that can have a higher temperature tolerance, or is it better to select larger genetic diversity to undergo this climate change selection?
Yeah, I think this is a pretty controversial topic, and there are lots of interest about assisted evolutions in particularly in the coral reef one because the urgency of dealing with that problems and using those non-conventional methods is even bigger for coral reef because we know coral reefs will be most sensitive to warming. But for fish, I think my own opinion would be that the strategy is to look at to target for a broader genetic diversity because we don't have a still good understanding about the whole complexity of genomes and how that would then emerge out as their phenotypes and the adaptation to environment, not just temperature, but other aspects of adaptation, and whether there is a particular trade-off between their thermal biology and other aspects of their biology. So I think in this case, by targeting a broader range of genetic diversity, then it will also promote higher rate of selections by the environmental changes. And what we did some theoretical modeling exercise trying to look at the rate of evolutionary responses to selections from warming using our model, a set of components of our model. And what we find is that in some conditions, some of the species may be able to respond quickly fairly quickly to strong selections from warming. And having a broader genetic diversity clearly, at least in the models, is one of the factors that the outcome is sensitive to. So with a broader genetic diversity, it can also increase the rate of selections. Yeah.
With respect to your suggestion about the coastal BC species moving northward, with respect to anadromous species, in particular, are you able to take into are you able to take into account the non-ocean rig side of it, the global warming impacts on the migration route?
Yeah, no, our model is not salmon specific, so we don't have that level of details for some of these anadromous species, particularly like salmon, where they have this really amazing life history of most of them going back to the natal river to spawn. So we mostly, this is kind of characterizing the ocean phase of the species, while we didn't account for the complexities in the freshwater phase. So if we add that, I think the vulnerability would be even higher because works by colleagues such as Scott King and people that shows that's a phase where there seems to be also additional vulnerability and risk to salmons because of warming in the river that would then affect the mortalities that they go into their spawning site or the reproductive output ultimately. Yeah. Yes.
I was very surprised when you presented one of your maps that there was insufficient data around Great Britain and in the Mediterranean Sea. When you were showing us whether it was climate
Yes.
overfishery
or
yes. I forgot what the third one
is temperature, primary productivity, and fishing efforts.
Right. Yeah.
Yes.
And So you seem to have data for like, I don't know, like Peru or
Yeah.
India or Madagascar, and
Yeah.
there was none for the Mediterranean
Yeah.
Sea and for Britain. I was a little
So,
surprised by that.
so that categories, the striped categories, shows either low data or are unable to differentiate the different factors. So in this case, in the Northeast Atlantic, particularly in North Sea and area, it is undetermined.
Okay.
We did a subsequent analysis that are being presented here that look at the more details about the time series data and how that relates to environmental change. And we find that, so for example, in the North Sea, at the beginning, it's really driven by fishing. And then the fishing effects increase. And then at some point, when the environments become almost fully exploited by the fisheries, the environmental effects becomes most important. But then after that, both fishing and environmental effects seems to interact with one another. So it's the mixture of that effects that becomes what we call the mixed effects, drivers. So both fishing and environmental change are almost equally important in the recent time. And in this particular, in the map that I showed you earlier on, because of that reason, it is not attributable to a single driver. But then in subsequent analysis, we are able to then tease out that more nuance about how fishing and environment, or in this case, changes in the temperature or pike protection is affecting the catches.
So could it actually be that you have too much data if it's harder to discriminate in that spot? Because that's probably an area where you have a lot more data than elsewhere. So maybe elsewhere, similar complex things are happening, but you don't have enough data to see it.
Yeah, and also I think it also relates to the history of exploitation in that area, because it's much longer history of exploitation. The system has been highly modified. So at least from the time series analysis, it shows that it makes the attribution much more complex because there are so much interplay between different human drivers affecting the ecosystem.
Dr. Cheung, you've given us a very interesting overview, and you've stressed the importance of hope for the future. And I wonder if you could comment a little bit on where there's hope in areas right on our doorstep, like Howe Sound.
Yeah. So I think the thing is that we are already the good thing is in these province, in the regions, there's good governance systems that for the oceans compared to a lot of the other regions. And for adaptations, that's the first things to do is that have that good ocean governance that would then be able to implement basic ecosystem approach to managing the fisheries, like ensuring the fish stocks are well managed, the habitats are protected, reductions in pollution and things like that. So that's kind of the basic thing. And then the recent kind of active actions by the governments to set up protected areas is also very encouraging. Particularly, we in that process is already actively thinking about how climate change. For example, we just started a project with the Canadian the wildlife associations where we help to provide some of the modeling exercise to see how the planned protected area would be adaptable to climate change. So we evaluate some climate scenarios and see how some of the scenarios of protecting the waters may actually affect the effectiveness, and see whether there are alternative configurations that would then help to ensure that at least locally the adaptations will be that the system capacity to adapt to these climate change will be enhanced. And then there is this, I think in this course, lots of scientific research are looking at this topic, how coastal habitats would contribute to building resilience, both in terms of the ecosystems as well as the dependent human communities. Like some ants work looking at kelp forests is really important, because that would then inform the decisions about how and where to do these active interventions to deal with these impacts. So I think there is a lot of there are the ingredient to make that happen, and I think I see that there is compared to a lot of the other regions, it is actually a really good opportunities to actually implement some of these solutions.
In your unit, are you looking at any specific projects currently? You, your colleagues, or any of your students?
Yeah, so we in British Columbia, we are looking at that project with SIPO about the protected area, and we also have a project in the Caribbean trying to address similar questions about. I just came back from St. Vincent last week. We had a workshop in there working with different Caribbean countries, trying to identify or characterize their vulnerability to climate change in terms of ecosystem and fisheries, and then from there trying to identify possible adaptation solutions for them. And then we just started projects with the World Bank, looking at the West African region. Again, there's another area that we highlight as the most vulnerable regions to climate change impacts. The idea would be that we can come up with some suggestions, science or evidence-based suggestions about what, if in the future the World Bank want to invest on adaptation, what are the key pathway that they can do in order to make the most effective outcome from that.
Is the World Bank doing anything specific on mitigation that you feel is relevant at the moment?
I mean, they are supporting projects that relate to mitigations, some of the blue carbon projects. So it's a lot about coastal restoration and protections of mangroves and seagrass. And so those are called blue carbon. And there are lots of projects, particularly in tropical developing countries. There are some, the World Bank is involved in some of those.
I take it that you're predicting some very dire consequences in the eastern Mediterranean. Does the relative isolation, lack of connectivity to open oceans, does that limit the adaptation?
Yes, it is because I mean, geographically, the Mediterranean is a semi-enclosed sea, and it's only the Strait of Gibraltar that allows species to exchange elsewhere. So there's a really limited pathway that some of the species can adapt by shifting their distribution, and some of them will, but not a lot. Particularly, say, in the eastern side, which is far away from the outlet. So there is already a strong signal of changes in ocean temperature, changes in species community structure and things like that in the Mediterranean. And some of that is also contributed by other human activities in the Mediterranean. That is really heavily used area. But just the climate cycle, because of that geography, it makes them really highly impacted area, and that's what we call it. I mean, in the literature, we call that cul-de-sac effects, where species are limited by the land boundaries and will be able to easily adapt by shifting their distribution. Yeah.
Sorry, I have a last question. So when you talk about the appearance of novel habitats, all of them were along the tropic, which makes sense, but you had one on Scandinavian waters,
yes.
which was a little surprising. So what's special about that area? Because I imagine it can't be just temperature, there has to be something else.
Yeah, so it's a combination of like temperature, oxygen, pH, sea ice, and things like that.
But do you have to remember what the data looked like there?
I don't remember what specifically drive that new combination.
Yeah, because there was really like a surprising hotspot over there.
Yes.
Or cold spot, I don't know how you would call it since it's
yeah.
Questions? No? Well, I didn't receive any questions from the online world, so, well, I just would like to thank William to make the effort to come here to the SFU campus. I know he mentioned he got lost right here. So, yeah, before I was forgetting something. Yeah, I also, as a token of our appreciation to come here and share your research with us. So
thanks so much.
Yeah, this is for you. And thank you, all of you, for coming. I am hoping to have, I am planning to organize, along with the Climate Future Initiative here at the SFU, other seminars. So I would love to have your feedback. So just send me emails and let me know anything that you would like to maybe for us to improve, or what topics would you like to see in the next series of the seminar series that I am planning to do for the fall. Okay, thank you so much for joining us.
Thank you so much.